We have been studying the one-dimensional harmonic oscillator, quantum harmonic oscillator. In the first lecture, we did the analytic solution. In the second lecture, we did the solution, representing the solution in the complex plane, and we discussed the generating function and the recursion relations and back to the differential equations again. Harmonic oscillator is an interesting problem because it lends itself to algebraic solutions, and today we shall discuss the algebraic solution, which is a very powerful method. Let me first start with trivial preliminaries, which we shall use along the way. For example, let A and B be numbers, and if we have A square minus B square, we write it as A minus B, A plus B. So this is the factorized form of A square minus B square. What if it's A square plus B square? We can write this thing as A square minus B square, and this is I square, I being the imaginary number. Therefore, this is A minus IB, A plus IB. So we shall use this thing. Second is the commutator. If you have two operators, A and B, then AB commutator is defined as AB minus BA. If the commutator is not 0, AB is not equal to BA. If it is 0, then it's like you can interchange the order. So, for example, if we are given AB and we would like to write it in the form of BA, we will do it like this: AB plus BA. So as you see, AB minus BA, that's back to that definition. We shall use this one a lot in the problem. And we will have more complicated commutators, and let me just write the main thing that we shall use. The order is important, so we open it up like this: AB C plus B AC, or if it is AB and C, this is A B C plus AC B. Let me show this. We can do this one. This is ABC minus CAB. Is this equal to that? This is ABC minus ACB. This is plus ACB minus CAB. So we have ABC here, that's right. CAB here, it is here, minus. And minus ACB plus ACB, they cancel. So similarly for this one. So we shall use this one a lot and these a lot. Okay? So this was just the algebraic preliminaries. Now to the physics problem. I am erasing this. The dimensionless form of Hamiltonian was H is equal to x squared over 2 plus p squared over 2. These are dimensionless. Which we can write as x minus IP over root 2 x plus IP over root 2. If x and p were just like numbers, then this would be okay. But they are operators and they do not commute. They have this fundamental commutation relation, I. So this is not equal to that. Let's see what this leads to. First of all, the square, we get the squares. So we have x squared over 2 plus p squared over 2. But then I plus I over 2 xp minus px. But this is just the xp commutator, which we give as I. So this is I. So that means we have subtracted in doing this factorization, we have subtracted from the Hamiltonian minus 1/2. And to get back to the Hamiltonian, we must add 1/2. Okay. So this is Hamiltonian minus 1/2. To that we add 1/2, so they cancel and we get back to this form. So we shall call this operator a dagger. We shall call this operator A. So the Hamiltonian, which is x squared over 2 plus p squared over 2, that's equal to a dagger A, and we add 1/2 plus 1/2. Now, this operator, first of all, it is Hermitian. It is called the number operator, n. Let me just indicate the operator like this. So n is defined as a dagger A. Therefore, eigenvectors of n are also eigenvectors of the energy. So we'll be trying to get the energies, eigenvectors, etc. using these algebraic techniques. So A comes with x plus IP. This is a dagger. I'm erasing everything. Let me write here. A is equal to x plus IP over root 2. A dagger is equal to x minus IP over root 2. N is equal to a dagger A. And let me just write this. H operator is n plus 1/2. Now let us look at the commutation relations of A and A dagger. A dagger, that's equal to root 2. This gives me 1/2. This is x plus IP commutator, x minus IP, and we remember xp is equal to I. Therefore, this is 1/2 times minus I times xp plus I times px. This is I, this is minus I. Therefore, it is 1/2, 1 plus 1, so the result is 1. So a dagger is equal to 1. Let us obtain the commutation relations with n. A is equal to, this is a dagger A. Remember the composite commutators I wrote at the beginning. So this is a dagger A, which is 0. Every operator commutes with itself, plus a dagger A. A dagger A, the order is changed, so we have a -1 here. So NA is equal to -A. If we just take the Hermitian conjugate of this equation, this is A dagger N is equal to -A dagger. If we change the order again, and A dagger is equal to A dagger. So let me just write these commutation relations here as a list. And A is equal to -A, and A dagger is equal to A dagger. All right. Now, let us discuss the eigen states of this operator. By the way, it's called number operator, and for reasons that will become clear soon. And let us suppose n is a Hermitian operator. N is an eigenvector of n with n. And we assume n's are properly normalized. So n, that's equal to n. This is just 1. And here it is. N is equal to n. But n has a particular form. It is A dagger A. So it is n, A dagger A, n, that's equal to n. This is telling us something important about n, because this is a vector like psi, and this is a vector not necessarily normalized, and this is a vector which is the conjugate of this. So it is psi. So it is basically a norm square, and that's equal to n. That means n has to be positive semi-definite, namely it's either a positive number or 0, but it cannot be negative. 0. Okay. I'm erasing this part. What is n, a, n? A, n is coming from here. Let's look at that. This is equal to n, a, n plus a, I changed order, n, n. This commutator we computed, that's minus a. So it is equal to minus a n. This is an eigenvector of the number operator with n. So it is n times a n, which is n minus 1 times a n. So n a n is proportional to the vector n minus 1. In fact, we even know the proportionality constant, because if it's something proportional to n minus 1, and this is also the same thing, conjugate, and it's giving me n, so I can write this as a n is root n, n minus 1. Where n minus 1 is the normalized state. So we let's remember, what do we know so far? We know that n is a positive number. And if this is an eigenstate of the number operator, an gives me another eigenstate with the eigenvalue n minus 1. Namely, the eigenvalue, the value of the eigenvalue is reduced by 1. So what about a square n? This is root n a n minus 1. And using the same formula for n minus 1, this is equal to root n minus 1 n minus 2. So it will go down. Now I have a state with the eigenvalue n minus 2. The eigenvalue is reduced by 2 integer units. Clearly this cannot go on indefinitely. Suppose we reach a, let's say k max n equals to root n minus 1 n minus k max plus 1 times n minus k max. Why am I calling the last one? Because further reduction should be impossible. If I reduce it by one more, it will be on the negative side. So let me say this is 0, this is 1, this is 2. So n was somewhere a positive number, and we were, by applying a, reducing the eigenvalue by 1 integer unit. So the last one, n minus k max, must be here. So probably it is like this. Okay. But now, what is the property of this thing? If a acts once more on this state, it will give 0. So I'm erasing this part. A n minus k max is equal to 0. Suppose this is correct. What is that eigenvalue? So let us apply n, let's call it n prime if you wish, n prime. This is a dagger a acting on n prime, and by definition a n prime is 0. So therefore this state n minus k max, we learn, has the is equal to 0. So we are not there, but we are right at the least possible value for n. So k max is equal to n. What do we learn from here? We came through integer steps, and the last step is 0. So let us write k max is n. N has the spectrum 0, 1, 2, 3, etc. And the value of the energy, E n, is n plus a half with n, all these integer values. So through purely algebraic manipulations, we got the energy and we got the energy eigenvalues for all states. Now, what we shall indicate this state A, so n prime is the value 0, so A0 is equal to 0. That's the, so this 0 is the ground state of the harmonic oscillators. So this is the 0 is the ground state of one-dimensional quantum mechanical harmonic oscillator. Before we go on, let's look at this wave function. What's this coordinate representation and momentum representation? For example, if I do x a 0 is equal to 0, this is a differential equation because a is a differential operator, x plus ip over root 2, and the coordinate representation of p is 1 over I d by dx. So this gives me x 1 over root 2 x plus I 1 over I d by dx, and x 0, let me call this psi 0 of x, is equal to 0. So that's the differential equation. So x psi 0 plus d psi 0 dx is equal to 0, or d psi 0 over psi 0 is equal to minus x dx. Integral, let's integrate. Log of psi 0 is equal to minus x squared over 2 plus a constant, but let me write the constant in a convenient way, log c0, and if you exponentiate it, this is psi 0 is equal to c0 times e to the minus x squared over 2, and if we normalize it, dx psi 0 square is equal to 1. That's equal to c0 square dx e to the minus x square, and this is root pi. So c0 is 1 over pi 1/4. So I can erase this part. So psi 0 of x is equal to 1 over pi 1/4 e to the minus x squared over 2. Of course, this is the same ground state we found by using the analytical methods. Let's also look at the wave function in the momentum space. So we just look for this one, PA 0 is equal to 0. Instead of x, I used, namely A0 is the null vector. I'm looking its P component. So A is over there. So this is 1 over root 2 minus 1 over I d by dp plus p psi 0 of p is equal to 0. Plus I times, here there's an I times p. So it is 1 over root 2 I p plus d by dp psi 0 p is equal to 0. I don't need to solve it anymore because if you just look at it, just replace x by p, it's the same differential equation, so I can even write the normalized wave function immediately. Psi 0 p is equal to 1 over pi 1/4 e to the minus p squared over 2. I remind you again that these are dimensionless variables. Okay, so we started with n, we reduced by a, the eigenvalue, we reduced it down to 0, that was the lowest eigenvalue of the number operator, and we obtained the wave function of the ground state in the coordinate space and in the momentum space. Now we shall look at going the other way, up, with the a dagger operator or the creation operator. Okay, I'm erasing this. Ground state are these just simple Gaussians. I can erase everything. So, again, I remind you that the lowest value of n is 0, but the lowest value of energy is not 0. It is 1/2. That is, you cannot make the particle completely stop in quantum physics. It has to jiggle. That's the big difference from the classical physics. Now we have the state, ground state 0, and now we have a dagger 0. Now what's that? We act on it with n to see what's that. Well, we use the commutation relation. That's n a dagger 0 plus a dagger n 0, and this is 0. And this was a dagger. So n a dagger 0 is equal to plus 1 times a dagger 0. So clearly a dagger 0 is proportional to 1. Namely n equals 1. Let's do one more. N a dagger square 0 is equal to n a dagger square 0 plus a dagger 2 n 0. That's 0 because of the a. It has a dagger a, and a kills it. Okay, and this is, now this is a composite commutator. We break it up. So it is a dagger and a dagger 0 plus and a dagger 0 equals, this is a dagger, this is also a dagger. So this is a dagger square 0, a dagger square 0, so it is plus 2 times a dagger square 0. So a dagger square 0 is proportional to 2. Clearly, a dagger n 0 is proportional to n. In fact, we can find the normalization constant. I'm erasing. So let's say a dagger n 0 is equal to c times cn times n. Or if I take the conjugate, 0 an is equal to cn star n. Let me multiply n from the right. Namely, I am applying n here. 0 an n That's equal to Cn star and n. But this is 1. And we did this before. Okay, this was bringing, so it was bringing n minus 1, n minus 2, n minus 1, which is just 1, times 0. So this is just root n factorial. So times 0. This is an 0. So if I multiply from the this by right, 0, 0 is 1. So root n factorial is Cn star. There is nothing complex here, it's real. So Cn is root n factorial. So if you look at here, we find n is equal to 1 over root n factorial, a dagger and 0. Okay, it's an important formula. I will erase it. The rest. In fact, we can now even look at the orthonormality relation. Mn would be 1 over root m factorial n factorial 0 am a dagger n 0. And this is simply n factorial over n minus k factorial, n minus m factorial, 0 a dagger n minus m 0. So a dagger acts on this one as if it is a. So for example, a0 is 0, but 0 a dagger is also 0. So a daggers act onto the left as a's act to the right on the ground state. So the only contribution comes from n equals m. In that case, a dagger to the 0 is 1. So we need n equals m. So if n equals m, this is 0 factorial. And m is equal to n. So these cancels. Therefore, the result is delta mn. So these states are orthonormal. Mn is equal to delta mn. Okay, I'm erasing this part. Now, we shall consider some commutators. Some interesting commutators. First, we know that a dagger is equal to 1. Next, a dagger square. So this is a composite. This is a dagger plus a dagger, a dagger. So this is 1, this is 1. So it is 2a dagger. Now let us assume a dagger n is equal to n a dagger n minus 1, because that's the way it seems to go. This was square, this is 2a dagger. This is a dagger, this is 1. Let us try, that's proof by induction, a dagger n plus 1. So a dagger n times a dagger is equal to a dagger n, a dagger plus a dagger n, a dagger. This is 1, and this we assumed this is n a dagger n minus 1. So the result is here I have a dagger to the n, here a dagger to the n. So it is n plus 1, a dagger n plus 1, which is a dagger n plus 1. So it checks. This is a general formula then. And it is important, let me write it here. A dagger n is equal to n a dagger n minus 1. I am erasing this part. Suppose there is a function of f of eta. Eta is some number that can be expanded in power series, k, ck, eta to the k. If so, we can talk about a function of f of a dagger, namely it has such a power series, k, ck, a dagger to k. Therefore, f a dagger from here, because f can be expressed as a power series. So it is something like delta delta a dagger f of a dagger. Because for every power we use that. Okay. So it's like the formal is a dagger n. An interesting example is a e to the lambda a dagger. This is exponential. Exponential can be expanded in power series, but simply this is the derivative with respect to a dagger, so it is simply lambda e to the lambda a dagger. If you want to see it more in detail, this is a 1 plus lambda a dagger plus lambda square a dagger square over 2 factorial. Last term I will consider lambda cubed a dagger cubed over 3 factorial plus 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 equals, the first term gives me 0 plus lambda times 1 plus lambda square times, this is 2a, so it is a dagger plus lambda cubed times a dagger square over 2, etc. Now you see it is lambda times 1 plus lambda a dagger plus lambda square a dagger square plus 2 plus etc. So it lambda e to the lambda a dagger. So this is an important result that we shall use later on. So this is the first group of commutators I want to discuss. Now the second group. So A dagger N, we already have it there. This is N A dagger, but now I am using their actions on the ground state, 0. So this is N A dagger N minus 1, 0. Now I will use A square A dagger N acting on 0. So this is equal to A dagger N 0 plus A dagger N times A here, 0. So this one is 0. We can write this one also. This is an operator. So it is A dagger N commutator plus acting on the ground state, 0, plus A dagger N A 0. So this is 0. You see, the advantage of considering these operators with acting on the ground state is that all those terms with A's to the right are giving us 0. So this is the contribution. What is that? This is the first one gives me N from here, and A dagger N minus 1. So let me write it. I will do it once because this is so easy. A dagger N minus 1, 0. So the second one is N minus 1, A dagger N minus 2. So it is N minus 1, A dagger N minus 2, 0. So in general, for example, A dagger N commutator 0 will be equal to, well, there will be many combinations, and in all of them except one, there will be A's to the right, which will kill the ground state, no contribution. So the only term, it will come from this k-fold commutator. Let's perhaps call it fully contracted. It is A, then again A. So this is the kth one, A dagger N, all these commutators acting on 0. So this is the only term that is contributing, and the computation is trivial because the first one gives me N A dagger N minus 1. The second one gives me the power, reducing the power. So this is what? This is N minus 1, N minus K plus 1 times A dagger N minus K 0. You can multiply it by N minus K factorial, divide by N minus K factorial. So it is N factorial over N minus K factorial, A dagger N minus K 0. So let me write it here. A to the K, A dagger n acting on 0 is equal to n factorial over n minus k factorial a dagger n minus k 0. I'm erasing. Okay, next I want to introduce something, then we'll take a break, and it is this. I can multiply n by a complex number lambda n, and this is, and divide by root n factorial 1 over root n factorial a dagger n 0 and sum over n. So this gives me sum over n lambda a dagger to the n over n factorial acting on 0. So this is e to the lambda a dagger acting on 0. So let me call this state psi lambda. It's not normalized. Let me just write it there. Not normalized. However, it's a, we can normalize it, of course. It's a very nice thing to have a generating. It generates these oscillator states. For example, psi lambda is sum over n. So this component is simply n. So it is lambda to the n over root n factorial times state n. So you can, by taking the derivative with respect to lambda n times and dividing it by root n factorial, you extract the harmonic oscillator state n. So it generates all those states. It turns out this is a very, very useful state. So it's the generator of the oscillator states. It's also called the coherent state. We shall discuss a lot about it. We take a short break now.